For the first half of this video, I'm going to go over scientific notation, and then I'm going to talk about Avogadro's number. It's important to have an understanding of what scientific notation is and how to write it in order to understand Avogadro's number. So here we have some examples of numbers. You should be able to understand what these are: 1,250, 3,500,000, so on and so forth. These are really large numbers or really small numbers. In the case of this one and this one, those are very small numbers. And so scientists have come up with a shorthand way of writing these numbers that communicates what the numbers actually are, but cuts out a bunch of zeros that are unnecessary for the actual use of the number. They just are placeholders to show you how big or small that number is. The shorthand is scientific notation, where the amount of digits in a number is represented by this 10 to the power of something, and the actual numbers, the significant figures, the significant numbers in that large number are represented as a whole number with some decimal places. So the gist of scientific notation is this: one number in the number will come before the decimal place, the rest come after, and it is multiplied by 10 to the power of something to represent the place value. The easiest way to do this is by moving the decimal place. Numbers here, like 1,250, have an implied decimal place that's at the end of the number. So you could say 0.0, same thing. If I move the decimal place over 1, 2, 3 times, that number would end up being 1.25. We can omit this 0 because it is not a significant zero. Don't worry too much about significant zeros. That's not something that I taught you, and that's okay. Then, in order to communicate to the person viewing this number that it is not actually 1.25, it is actually 1,250, you have to multiply that by the amount of times you move the decimal place. So I moved it 3 times. It's a positive number because the number is big. So you can see for 3,500,000, that becomes 3.5 times 10 to the 6th power. This becomes useful when you are doing exponential math, because when you multiply or divide exponents that are with the same base, 10, the number manipulation of the exponent is a plus or a minus. So it makes that math easier, where all you have to do is the math with the front number and do a little quick exponential math. So if you are competent at exponential math, using it in significant notation makes that math simpler. Because these are large numbers, these are all positive exponents. When we get here to a very small number, and a really, really small number, the exponent becomes negative. That denotes that the number is very small. So in this case, I'm moving the decimal place 1, 2, 3 spots to the right, making this -3. And on this number here, 1, 2, 3, 4, 5, 6, 7, 8, 2.66 times 10 to the -8th. So that is scientific notation. The other part of this table is the calculator display. Because you'll be doing some math with numbers that have exponents in it, like Avogadro's number, you need to understand what the calculator is telling you. This e here is equal to 10 to the power of whatever the number is that comes after it. That's what that means. The e is equal to 10 to the power of whatever number comes after it. You can find this little E button on your calculator. It'll say EE. And so that's actually an easier way to write the number in. Instead of writing times 10 to the power of something, you can find this EE button generally on a graphing calculator and use that. And that is a nice shorthand, but you don't have to. So part 2 is practice. Don't use a calculator here. You should be able to do this by hand. I'm going to do the first one with you, and then you need to do the rest. So pause after I do the first one and fill in the rest, and then I'll show you what the answers are. So I have 4,200. My decimal place is at the end of the number. I move that over 3 times, and the scientific notation is 4.2 times 10 to the +3 power. And my calculator display omits this part here and becomes 4.2 little e 3, like that. Pause here and try the rest of these problems. Here are the answers to this problem. For the next part, you need to pause and read the little skit, Mr. Toad and Molly. So do that now. So let's look at the first problem together. According to Mr. Toad's decree, there are 600 million, billion individual things in a mole. Attempt to write out this number in longhand. Then write it using scientific notation. You'll see why when you write this number out, why scientific notation is really more useful than the whole number. So we start out with 600, and then according to our note here, a million has 6 zeros, so I'm going to add 12 more zeros. And then a billion is 9 zeros. And you can see that is a really large number. If we were to write this in scientific notation, we would count the amount of zeros, which is 23. And that will get us 6 times 10 to the 23rd. This value, the number of molecules in a mole, is called Avogadro's number. In reality, this is the number of anything in a mole. The amount of atoms, the amount of particles, the amount of molecules, the amount of ions. That is the amount in a mole. It's like a dozen is worth 12. A mole is worth 6.022 times 10 to the 23. So in reality, the more exact Avogadro's number is 6.022. I often use 6.02 times 10 to the 23. 6 times 10 to the 23rd is also used. These will all get you a relatively correct answer. But if you would like to be as exact as you can, this is the most exact one that we will use. There are more digits that come after the last two, but they are not as significant, so it's okay to leave those off. So what do we do with this number? It becomes another conversion factor. 1 mole of something has 6.02 times 10 to the 23 things in it. So let's say we were looking at magnesium sulfate dissolved in water. And let's say in this sample, I put in 0.5 moles of magnesium sulfate. I can use Avogadro's number and calculate how many molecules I put into the water. So it would look like this. Start with your given number. And then I use this conversion factor. Remember, your conversion factor has to cancel the unit, top and bottom. So I'm going to put Avogadro's number on the top. I'll be very exact with our labeling here. Over 1 mole of magnesium sulfate. These will cancel. I'm left with molecules, which is what I want from this question. You can see it's another conversion factor. Here's where, if you're clever, you can get away with doing the math without actually using a calculator. I can multiply these numbers and ignore the exponent for now. So half of 6.02 would be 3.01. And this number doesn't change the place of the decimal, so the exponent is going to stay the same. Half of 6.02 times 10 to the 23rd is 3.0 times 10 to the 23rd. If any sort of math were to move the decimal place one way or the other, you can adjust the exponent up or down. If you know how to do this math, it becomes much more simple than putting it into the calculator. And this is how many molecules of MgSO4 that I put into this solution of magnesium sulfate. Complete the rest of the assignment, and you should have a good understanding of how to use Avogadro's number as a conversion factor.